Hello, I'm Rebecca Barnes. Welcome to the Science ESA vodcast. In this episode, we will investigate the infrared universe, explore discoveries made by groundbreaking infrared space missions, and take a look at Herschel, ESA's pioneering infrared space telescope. Most of the information about the physical nature of the universe comes to us in the form of electromagnetic radiation, which celestial objects emit at various wavelengths. One way to analyse this radiation is to study the spectrum. Astronomers use a spectrometer to spread the combined radiation received from a celestial object out into specific wavelengths or specific photon energies.
Atoms and molecules can emit and absorb light, leaving a signature in the spectrum in the form of a characteristic pattern of lines. If a cooler gas lies in between us and a hotter source of radiation, the atoms and molecules will absorb certain photons. This produces an absorption spectrum, where gaps appear at specific wavelengths depending on which atoms and molecules are present in the gas. An emission spectrum occurs when atoms and molecules in a hot gas emit a photon with a specific energy or wavelength. The bright lines are again unique signatures of each atom and molecule.
Another way to present a spectrum is to plot the intensity of radiation as a function of wavelength. Signature absorption and emission lines of atoms and molecules will also appear on the plot. The life story of an object can be read from its spectrum. In addition to learning about the composition of an object, astronomers can study its spectrum to find out its temperature, density, and motion. If we go beyond the red part of the visible spectrum, we enter the realm of the infrared. Often, infrared is described as heat that is radiated from an object. But what is important to realize is that what we would consider to be cold is also an emitter of infrared radiation. Celestial objects that emit in the infrared have a temperature between room or body temperature and a few degrees above absolute zero, and therefore a wavelength that is longer than visible radiation. Observing the universe in the infrared allows astronomers to explore the cool universe. Studying atoms and molecules in a region of space provides vital information to build understanding of how planets, stars, and galaxies are formed. Emission and absorption lines for virtually all molecules lie throughout the infrared portion of the spectrum. This means that infrared spectroscopy is an extremely important way to detect these chemicals in the cosmos.
The infrared portion of the electromagnetic spectrum can be divided into three regions: near, mid, and far infrared. As a celestial object cools, it will emit most of its radiation at progressively longer wavelengths, and therefore further into the infrared. Near infrared refers to wavelengths that are just longer than those in the visible spectrum. In this region, cooler red stars become more prominent, and interstellar dust becomes transparent. These infrared waves can glide through thick regions of dust that often envelop many celestial objects, such as infant stars. In the mid-infrared, the cool interstellar dust itself starts to shine. Astronomers can also study emission from disks of material that surround newly forming stars, which one day may develop into new planetary systems. Many objects in our solar system also emit radiation in these wavelengths. The very long wavelengths of the far infrared are emitted by extremely cold matter. In this portion of the spectrum, astronomers can detect the cold radiation from protostars and peer into the centers of galaxies, including the Milky Way.
Observing the infrared universe from Earth is extremely difficult. The light at almost all infrared wavelengths is absorbed by molecules in the atmosphere. And there is another big problem. The atmosphere emits infrared radiation too, drowning out that of the target celestial object. the clearest view of the infrared universe can be achieved from space. In 1983, the first infrared space telescope was launched. This 10-month mission was a resounding success. The Infrared Astronomical Satellite, or IRAS as it was called, completed the first infrared survey of the entire sky. IRAS discovered hundreds of thousands of new infrared sources and 6 new comets, as well as finding warm but largely invisible dust coming from nearly every direction of the sky. IRAS also presented astronomers with the first ever images of the centre of the Milky Way, a view that is blocked in visible light by a dense fog of gas and dust. Before IRAS was even launched, ESA was planning its successor, the Infrared Space Observatory, or ISO. ISO was the world's first general-purpose infrared space observatory and was a truly outstanding accomplishment. With the wealth of data collected by ISO, astronomers continue to make new discoveries long after the satellite ceased to operate. Let's take a look at a few of them.
ISO detected water, an essential for life throughout the universe, for the first time. In our local neighborhood, water was detected in the atmosphere of all the outer planets as well as on Saturn's intriguing moon Titan. In the constellation of Orion, water was found in a remarkably high concentration. Dust and gas fills the space between stars. This is the interstellar medium. ISO found that this medium contained a carbon-rich material called polycyclic aromatic hydrocarbon. Here on Earth, these molecules are used as biomarkers. In space, they indicate organic chemistry and can be used to explore the basic building blocks necessary for the possible presence of life elsewhere in the universe. ISO observed over a dozen star-forming nebulae, penetrating their shroud of gas and dust to expose processes and young stars hidden inside. ISO made a huge contribution to understanding the history of star formation and discovered that there was a peak of star formation about 3 billion years ago. This discovery came about because the infrared revealed active star formation that had been largely obscured from visible observations by the diffuse interstellar material of the galaxies. Andromeda is one of the closest galaxies to our own and considered to be a typical spiral galaxy. However, ISO discovered that it was made of several concentric rings of very cold dust at around 13 Kelvin, too cold to be seen at visible wavelengths. In a nearby elliptical galaxy, radio observations had shown fast-moving jet streams of plasma released from the center of the galaxy. But until ISO was launched, it was not possible to see through the cloud of gas and dust in front of it. ISO revealed that the central object is a black hole.
After ISO, 2 other infrared space telescopes were launched. The Japanese Akari, for which ESA is supporting the data processing, and NASA's Spitzer Space Telescope. New discoveries led to an even deeper understanding and provided new questions to answer. These previous infrared satellites provided astronomers with a glimpse into the infrared universe. To learn more, astronomers need a telescope large enough and sensitive enough to gather the light that has travelled from the very faintest, most distant galaxies. ESA's Herschel Space Observatory is the largest space telescope ever, the first of a new generation of space giants.
The 3 scientific instruments on board Herschel have a far superior sensitivity and resolution than previous infrared space telescopes. The Photoconductor Array Camera and Spectrometer, or PACS, is a color camera and imaging spectrometer. PACS can study young galaxies and star-forming nebula. It is the first instrument capable of obtaining the complete image of an object at once. The Spectral and Photometric Imaging Receiver, or SPIRE, is designed to exploit wavelengths that have never been studied before. It is a color camera and spectrometer and can study the history of star formation in the universe. The heterodyne instrument for the far infrared, or HiFi, is a high-resolution spectrometer. It is also designed to observe unexploited wavelengths and is able to identify individual molecular species. These are fundamental in the study of solar system objects, star formation, and galaxy development. The instrument detectors are cooled to a temperature close to absolute zero by a cryostat of helium that sits underneath them. The instruments and the cryostat are surrounded by thermal shields. This is the payload module of Herschel and is located underneath the huge primary mirror. The service module, housing the instrument's electronics and communications hardware, sits below the payload. Herschel's primary mirror is more than 4 times larger than any previous infrared space telescope and can collect almost 20 times as much radiation. The mirror is so perfect that irregularities on its surface are less than 1,000th of a millimeter high.
Herschel will probe deeper into the infrared than ever before, and it will open a completely unexplored infrared window onto the universe. Over half the energy in the universe that has been created since the time of the cosmic microwave background has now been reprocessed into infrared. Herschel will observe the peak of the spectrum of this light, bridging the gap between wavelengths used to detect the cosmic microwave background and shorter infrared wavelengths. Observations in this region of the infrared spectrum will provide crucial information about the history of star formation in the universe. Through the spectrum, Herschel will be able to identify the peak in star formation that occurred a few billion years after the Big Bang, and may tell what sort of galaxies contributed to this peak. As well as this, Herschel will study the formation and evolution of galaxies. Currently, it's not known if all galaxies form in the same way. Closer to home, Herschel will investigate the process of star formation in detail and take a census of ongoing star formation within our galaxy. Besides this, Herschel will explore the cold, dark bodies of the outer solar system and the chemistry of atmospheres of objects such as comets and planets. The Herschel Space Observatory will open a new window onto the universe, which could lead to thrilling discoveries that cannot be predicted. The entire story of the evolution of the universe is told through the electromagnetic spectrum. Each mission that covers a different portion of the spectrum plays a unique role in telling this story, or tells a different part of the story. The pioneering Herschel Space Observatory is set to further revolutionize our understanding of the cosmos. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.